Welcome to Chemistry at Amanega High School. I'm Brian Brown, and today we'll be looking at our first set of notes over Chapter 14, which deals with gases and gas laws. Now, last chapter we looked at all the different states of matter. We introduced the idea of kinetic molecular theory as it applies to gases. Well, because gases have no attractive forces existing, or they're negligible because of the kinetic energy and the distance apart of the molecules, gases are very predictable in their behaviors. And what we're going to be looking at in Chapter 14 is really gas behavior. Now, 14.1, your book introduces properties of gases. And what we're really doing here is revisiting kinetic molecular theory and applying it to gases. Now, one, remember that particles were far apart and had negligible volume. They move in rapid random straight line motion. They collide elastically, so when they collide, there's no net loss in kinetic energy. And they have no attractive or repulsive forces. And really, it's negligible attractive or repulsive forces. So those are our fundamental properties by which gases behave. Now, if you extend those properties and you take a look at different types of things we can measure about gases, then what we're really going to be doing is looking at relationships between different gas law variables. Now, what are the variables we're going to be studying in this chapter? Well, one of the most important is pressure, and we talked about this last chapter. Pressure is caused by the collisions of particles against a surface, and it's the force of those collisions divided by the area over which they occur that gives us pressure. Now, kilopascals is one of our most common units of pressure because Pascal is our SI unit of pressure, but sometimes we'll also see atmospheres and millimeters of mercury. Now, our second gas variable that we're going to talk about, which is volume and always has the symbol capital V, will be looking at the volume of the gas. Remember, individual gas particles have a negligible volume, but the gases themselves occupy the volume of the container. Now, a lot of the time we'll be measuring that in liters, but that's not the only unit we use. Quite often we'll also be seeing milliliters. And there are certain situations where we end up having to convert things into liters just so that we have consistent units. Third thing is temperature, and that would be variable T, so you write it as a capital T. Unlike the others, we're going to have one unit of temperature that we need for all of our gas law problems, and that's the Kelvin unit. So don't forget, in order to get temperature from Celsius to Kelvin, we have to add 273.15, and don't forget, you need to round appropriately, and that's one of the things you'll be practicing with our math review for the chapter. So one of the things that separates temperature from the others we've looked at so far is pressure. We've got 3, and there's actually more than that. In volume, we typically look at 2 different types of units, but when we're dealing with temperature, we're always going to have one unit. Always, always, always convert to Kelvin. So whenever you're looking at any gas law problem, if you see Celsius, change it to Kelvin before you worry about doing anything else. And then finally, the last variable that affects gas behavior is the amount of gas itself. And that we're going to give the symbol N, which represents the number of moles of our gas. And remember, this is the mole we've been talking about the last 4 or 5 chapters. So it's the number of particles, and it's rounded to it's written in a convenient unit called mole because the actual number of particles is gigantic number. So remember, like when we're measuring how many donuts we've got, we convert that into dozens. When we're looking at atoms, we're going to be dealing with moles. So these are the 4 variables that can affect gas behavior. And what we're going to be looking at is different mathematical relationships between sets of these variables. Now, one of the things that you're going to see from time to time in this chapter is a acronym STP. Now, if you know anything about cars, no, we're not talking about motor oil here. What we're talking about is standard temperature and pressure. And this should look familiar because we started to see this in our discussions from last chapter when we talked about gases. So standard temperature is considered to be 0 degrees Celsius. Now, since in math problems we need to be in Kelvin, remember that's actually going to be 273.15 Kelvin that we'll be using. So whenever you see Celsius, you've got to get to Kelvin, and that means add 273.15 and round appropriately. The standard pressure is 1 atmosphere. And remember, atmospheres are a convenient unit because 1 is like our normal atmospheric pressure at sea level. So if you see 2, I think it's easy for most people to think, okay, that's twice normal pressure. But a lot of times we're going to be in kilopascals for problems. So in kilopascals, our standard pressure is 101.3 kPa. So standard temperature and pressure are an implied set of conditions that are sometimes going to be given in problems. So whenever you see the STP, you know you've got 273.15 K and 1 atmosphere or 101.3 kilopascals. Get used to STP, so whenever you see it, remember they're telling you a temperature and pressure indirectly. Now, One of the guiding principles of gas behavior is what's known as Avogadro's principle. And what Avogadro found was that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. So this is a relationship that's looking at the volume, the temperature, and the pressure, and the number of particles, which we're typically going to deal with in the number of moles here. So this is a relationship dealing with those things. And in fact, if we can measure volume, temperature, and pressure, we can use that to figure out what's happening with particles. So if you look at this situation in the picture here, notice the volumes all look the same. Well, when you check out volume, they're all 22.4 liters, which should be familiar from last chapter. Next, what would they weigh? Well, while they all have the same volume, they weigh differently. Well, that's not a surprise because remember, different atoms weigh different amounts. So 1 mole, which is what 22.4 liters of a gas at STP represents, notice they're all 1 mole. So they have the same number of particles, they just have different masses. And also notice they're all at 1 atmosphere pressure and they're all at the same temperature. So what this is saying is while the masses are different, when you have the same volume, pressure, and temperature, notice you had the same number of particles, 1 mole, or as we would convert that to if we ever needed to, 6.02 times 10 to the 23rd of those particles. So Avogadro's principle is one of the guiding principles that involves gas behavior. Now, another common thing that we're going to be discussing in certain gas law situations deals with how much of the gas we've got. And one fundamental thing you should understand is all other things being equal. In other words, if our volume and temperature is not changing, as the number of particles increases, we're going to get more collisions. That means we're going to have a higher pressure. So this is a relationship that should be fairly intuitive. As N goes up, P is going to go up for a gas. And consequently, if we look at the flip side, as N goes down, that would also mean P should be going down. So as we create a vacuum and we're moving gas particles, the pressure is getting lower and lower and lower and lower. So the number of moles and the pressure of a gas at constant temperature and volume are directly proportional to each other. As one goes up, the other goes up. So consequently, if we have a rigid container of fixed volume and we're not doing anything to mess with temperature, as we keep pumping gas particles into this container, the pressure is going to build. And eventually it could build to be a high enough pressure to actually rupture the side of the container. And on the flip side, if we started at 200 kPa and we reduced some of the particles, we would expect the pressure to drop as well. Now, the next relationship we're going to look at is the volume and its effect on pressure. And one of the things that scientists quickly realized was that as volume increased, the pressure decreases. So as you spread out a gas, you're going to get fewer and fewer collisions against the wall of the container because in a larger volume with the same number of gas particles, those gas particles are going to be more diffuse and spread out and scarce. So that would mean that our pressure is going to drop. So this is another one between volume and pressure that should be intuitive. So when volume goes up, our pressure goes down. This is a different type of relationship than the last one we looked at, where one went up, the other went up. This is what we call an inverse proportionality, and we're going to talk more about that in the future. In fact, this relationship actually has its own name, and it's going to be the first relationship we study. Now, if the volume going up causes the pressure to drop, when we compress a gas into a smaller volume, we would expect the pressure then to increase. And once again, you can see they're inversely proportional to each other. When one's going up, the other one's going down. So inside this container, if we decrease the volume by pushing down on the piston, we would end up with a higher pressure inside than we had before. Now, the next relationship that we're going to look at with pressure is temperature. So what is the relationship with temperature? Remember, as we heat up a substance, we make the particles move faster. So that's adding more kinetic energy. Well, that's going to cause the collisions to happen more often and with higher energy. So when temperature increases, the pressure should increase if volume and the number of moles are held constant. And this is another relationship that has its own name that we're going to end up studying in a few days. So the temperature pressure relationship is when temperature goes up, pressure goes up. This is kind of like the NP relationship we looked at earlier, and that they're directly proportional to each other. When one goes up, the other goes up. When one goes down, the other goes down. So if I had this cylinder with gases in it, and in situation B here, I apply heat, that's going to speed up the gas particles. Notice they're colliding more often with the side of the container, and they're also going to be colliding with more energy. That's going to create a greater force. Those are going to cause the pressure to go up. Now, that ends our notes for the first day. Good luck.